Have you ever wondered what the letter number markings mean on the side of amateur rocketry motors? And how can we use the information that's on these codes in order to design for our rocket vehicles? Well, the purpose of these codes is actually just to describe the behavior of the rocket motor. And there are three types of information that are being conveyed in that code. Number one, the energy of the motor. Number two, the average thrust of the motor. And then finally, the delay the motor will have before it ignites the parachute charge. The first part of the code is just a letter, starting from A and then going on from there, which describes the energy that the motor has. Rockets with more energy will have a letter which is further down the alphabet. But what does the energy of a rocket motor really mean? In rocketry, we measure the energy that a motor has in terms of impulse. This is just a multiplication of the thrust that the rocket provides with the time that the motor is providing that thrust. A typical thrust profile for an amateur rocketry motor can be seen here. To find out the impulse of the motor, we just need to look at the area that's underneath this thrust profile. The more energy that the motor has, the higher it'll be able to push the rocket. The scale that is universally accepted, and the one that gets printed on these rocket motors, works on the principle of doubling. So this means that for each letter greater that you have on the scale, there's going to be twice as much energy that's in the motor. For example, if we take a Class A motor, which is the one that's right here, this has an impulse of 1.26 to 2.5 newton seconds of energy. And if we were to upgrade that to a Class B motor, that means it would have anywhere from 2.51 to 5 newton seconds of energy. This doubling will continue all the way up until you get to the letter Z, and then it keeps on going after that, now just using 2 letters to describe how much thrust there is. So we can actually use the scale to also describe professional rockets. The highest rocket that you can buy on the commercial market, though, is only a Class F motor, which is anywhere from 40 to 80 newton seconds of energy. For context, the Transcendence vehicle, which ASTRA is building in order to get to the Kármán line, is actually a Class S motor with 361,000 newton seconds of impulse. This means that it would take at least 4,500 Class F motors just to equal one Transcendence vehicle. The next part of the code is a second digit, which is always communicated right after the letter, and that is telling us what the average thrust of the rocket is in newtons. And for those who are in America and don't know what a newton is, about 5 newtons makes 1 pound. So you can just divide any newton value by 5 and then it'll tell you how many pounds of thrust it's delivering. And of course, we have to remember that this thrust is an average thrust. So because it's a solid rocket motor, the thrust varies quite a lot during the burn. So it's actually just an average of the thrust that you're getting when you look at that number there. But you may have noticed that actually rocket motors which have the same class, like for instance Class C, might have different values for the average thrust they're showing on their rocket motor. So here we have a C2 motor and we have a C6 motor. So what does that mean? How can they have different thrusts if they have the same energy? Well, basically what this means is that for the motor, which is a C2, it will burn with 2 newtons of thrust, but it will just burn for longer. Whereas with the C6 motor, it will burn with 6 newtons of thrust, but for a third of the time that the Class 2 motor would have been burning that hard. So in the end, they have the same energy, but they just have a different delivery of that energy in a different time frame. So why is it important that we have these 2 different options where we could have a high thrust for a short period of time or a low thrust for a longer period of time? Well, the advantage really comes when you're dealing with optimizing for the weather conditions. So for instance, if you have a really windy day, it really helps to have a higher thrust at the start because it makes sure that your rocket is more likely to fly straight instead of getting kind of buffeted in the wind, and it'll point into the wind and then end up going somewhere else. If you're not moving as fast, that effect will be stronger. So it's better to have a higher thrust. But if you're in fair conditions, well, you don't have to worry about the wind so much, so it's actually better to have a slightly longer burning motor so that you don't get to such a high speed so quickly, and then you won't experience as much drag. And then you'll fly a little bit higher than you would if you had all that thrust all at once and having more speed at the start. The last part of the rocketry code is actually just the number that comes after the dash in the motor code. And what this is telling us is the time between when the rocket finishes burning the propellant and when it'll basically ignite the charge which deploys your parachute. So why is this important? Well, it turns out that the fastest speed that your rocket gets to is actually when the propellant has just finished burning. Well, this makes sense. But obviously you don't want to deploy the parachute right then, because the speed that your rocket is going could actually damage the parachute. And also you'll miss out on some altitude because the parachute will slow your rocket down too early. So it's better to have a little bit of a delay between when you end the burn and when the parachute gets deployed. To calculate the optimum delay time, you want to take the speed that your rocket will be going when it finishes burning the propellant and divide it by the gravitational acceleration of the Earth, which is 9.81 meters per second squared. Of course, you have to find the velocity of your vehicle in meters per second. You can find some conversions for that if you're working in feet per second in America. But yeah, if you find that duration, then that will be the optimum delay duration that you can have for deploying the rocket. So yeah, there's all kinds of different delays you can get. You can get, like, this one's a C6-5, so it'll have a 5-second delay. But of course you can also get different kinds of delays. This is a A6-4, so it has a 4-second delay. And you can even get zeros if you want. This is a C20. So yeah, that's an introduction of how to interpret the codes that are on your rocket motors. So I hope that you're empowered to go out and design your next rocket. And remember, to keep expanding your horizons.
I wanna be the best in the game, invest in my name, check no restraints, I'm obsessed with the pain, I ingest, I retain, assess and I change, possessed by the thought I'll be free one day from society's restraints, money, clout, and fame.